Welcome to today's Explainer. Today, we're diving into the hidden mechanics of the month. We're going to bypass those neat, perfectly square little grids on our desk calendars, and instead, we're going to look up. We're going to look at the massive, intricate, constantly moving celestial gears turning above our heads that actually make this whole system work. Okay, let's dive right into this with a seemingly simple question. How long is a month really? We've all been conditioned from childhood to rely on standard 30 or 31-day blocks, right? We just neatly tile them together to form a year, and that's that. But the true astronomical reality, it absolutely refuses to be boxed into a clean, whole number like that. 29.53059. That right there is the exact average length of a synodic month in days. If we take that incredibly precise, kind of messy decimal and break it down into human time, we are looking at exactly 29 days, 12 hours, 44 minutes, and 3 seconds. When you contrast this highly specific, uneven string of numbers with the neat, predictable calendar blocks we use every single day, you can immediately feel the tension. The universe, as it turns out, really doesn't care about our love for round numbers. So, to truly understand where that wild number comes from, we have to define what a synodic month actually is. By definition, a synodic month is the time between successive new moons. This is the single most commonly recognized lunar cycle in human history, and it's the absolute bedrock basis for lunar calendars globally. So when we're talking about this abstract conceptual thing called a month, we're actually anchoring it to something tangible. We're anchoring it to a physical cycle of the moon passing through its phases, something you can literally walk outside and observe in the night sky for yourself. But to really grasp the mechanics of this, we need to compare two totally different ways of measuring the moon's journey: the synodic month versus the sidereal month. A synodic month measures the moon's position relative to the sun. A sidereal month, on the other hand, measures the time it takes the moon to complete one orbit around the Earth with respect to the distant background stars. And here is the truly fascinating part. The synodic month is actually longer than the sidereal month. Why? Well, because the Earth isn't just sitting still in space while the moon orbits us. Earth is simultaneously hurtling through space, orbiting the sun. And this brilliantly illustrates just how dynamic our solar system is. Picture it like a giant cosmic racetrack. The moon completes its 360-degree orbit around the Earth. That's our sidereal month. But during that exact same time, the Earth has simultaneously moved forward along its own massive track around the sun. Because the Earth's position relative to the sun has changed, the moon literally has to travel a little bit further. It has to run extra distance just to catch up and properly realign with the sun to create that next new moon. That extra catch-up time, that is exactly what creates the synodic month. Now, if you thought 29 days, 12 hours, 44 minutes, and 3 seconds was complicated enough, let's go ahead and introduce the bug in this system: the time shift. Individual synodic months are not constant, not even close. In fact, they can vary from that mean average we just talked about by up to 7 entire hours. Our cosmic clock is constantly fluctuating. Every single month is literally a slightly different length than the one that came right before it. Now, what's really interesting about this is the sheer number of variables causing this 7-hour wobble. It's basically a perfect storm of physics. First off, the moon's orbit around the Earth isn't a perfect circle. It's elliptical, like a stretched out oval. Second, the Earth's orbit around the sun is also elliptical, and as they make these oval-shaped journeys, they're experiencing gravitational perturbations, which is really just a fancy way of saying they're getting tugged and pulled by other celestial bodies in the solar system. Finally, all of these factors combine to constantly alter the moon's orbital speed. It's not a smooth ride, it's a highly erratic dance. Let's look a little closer at that shifting speed, because it's wild. Since the moon's orbit is an ellipse, its actual physical distance to Earth changes throughout the month. When the moon is at perigee, meaning it's at its closest point to the Earth, the gravitational pull is stronger, so it physically moves at a faster speed. Conversely, when the moon is at apogee, which is its farthest point from Earth, it moves at a slower speed. Imagine driving a car around a track, but you're constantly stomping on the gas pedal and then letting off the gas every single lap. This constant speeding up and slowing down makes the math of a quote-unquote standard month incredibly complicated. And as you might guess, this mathematical mismatch builds into a massive issue for human history. I call it the calendar conundrum. For ancient civilizations trying to track agricultural seasons, you have to remember the sky was literally their only calendar. But they faced this glaring mathematical reality. A solar year, the time it takes Earth to orbit the sun, which is what dictates our seasons, is not evenly divisible by a whole number of lunations, or lunar months. They just don't fit. If you just stack lunar months together indefinitely, you will eventually fall completely out of sync with the solar year. Without adjusting it, your summer harvest season would mathematically drift right into the dead of winter. So the crucial point is how different global cultures actually stepped up to solve this astronomical bug. We see just incredible ingenuity and human adaptation here. Luni-solar calendar systems, like those developed by Chinese, Hebrew, and Hindu cultures, found a way to patch this drift by occasionally including what are called intercalary months. This effectively forces the lunar calendar back into alignment with the solar year. On the flip side, a purely lunar system, like the Islamic calendar, embraces that drift entirely. This means its months cycle freely through the solar seasons over a period of roughly 33 years. Let's unpack that first solution real quick. Intercalary months. This is just a brilliant synchronization tool. An intercalary month is quite literally an extra inserted month. Just like we insert a single leap day into February every 4 years to fix our modern solar calendar, the Chinese, Hebrew, and Hindu luni-solar systems insert entire leap months into certain years. By doing this, they successfully keep their agricultural cycles and their seasonal festivals strictly tied to the sun, all while maintaining the integrity of the moon's irregular changing phases. Now, contrast those adaptations with the Islamic calendar, which takes an entirely different philosophical and mathematical approach to the problem. It is one of the very few purely lunar calendars still in widespread everyday use today. It doesn't use intercalary months at all. Because a purely lunar year is mathematically shorter than a solar year, the Islamic months actually migrate. If a specific month lands in the blistering heat of summer this year, gradually, year by year, it will shift. It'll move through spring, into winter, and autumn, taking about 33 years to complete one full, continuous cycle through all of the solar seasons. We started this explainer by looking at a simple, neat calendar grid on a wall. And we've ended up uncovering shifting orbital speeds, gravitational wobbles, and millennia of human ingenuity just trying to mathematically tame the sky. So I want to leave you with this final thought to ponder. If our cosmic clock is fundamentally this chaotic, shifting by hours, and outright refusing to align into neat whole numbers, what does that say about our modern obsession with keeping perfect, rigid time? Think about that the next time you look up at a new moon. Thank you so much for joining me for this explainer, and keep exploring.